So this paper presents this new design for shared log, which is SCA log. So 1 minute. So just an overview, what are logs? They are like, if you see, they're like set of ordered records, and it allows the clients to read and write concurrently on top of it. So, so what are shared logs then? And what are the challenges with the shared logs? So the paper presents that mainly there are two challenges with the shared logs. So one is the scalability and total order. So like maintaining the total order of the records across the shards is a challenge, and it becomes more challenging with scale as the scale increases. And second is reconfiguration. So reconfiguration, as in if a shard is removed or if a shard is added or if a machine is added, so there should not be any downtime experience for the client. So and this becomes, to achieve this also becomes challenging with scale. So these are the two problems this paper addresses. So this is the basic design for a shared log. So how it is achieved. So this is the client, and this is the ordering layer, and these are the shards. Okay. So if you see, 1 minute. So client sends data to the ordering layer, and then the ordering layer orders the data, the records, and sends it to the shards. So this benefit of this approach is that since there is a ordering layer in between the client and the shards, so client doesn't know about the shards. So even if any shard is added or removed, so there will not be any problem with reconfiguration or downtime due to reconfiguration. But there is one problem, that this ordering layer can be a bottleneck for the throughput. So because it's a single layer in between the client and the shard. So to correct this one, there came another improvement, the state of art Corfu. So how Corfu corrects the bottleneck is that first the client sends the request to the ordering layer. Then the ordering layer sends back sequence number to the client. And then the client directly sends, using the sequence number, data to the shards. So thus the ordering layer doesn't come in between the client and the shards. So it doesn't act as bottleneck here. But then it creates another problem that was not there, that is the reconfiguration. So reconfiguration, that is if any shard is added or removed. So client, there is a mapping which maps the sequence number and the shards. So that mapping is maintained and is consistent between the data servers and the client. So when any like server is added or removed, this mapping has to be updated. So due to that, there is a downtime in between till the time the mapping is consistent between client and the server. So 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 now there is no less problem with the throughput, but there is this problem with reconfiguration. So this paper addresses this problem, and it comes with this SCA log. So that is an improvement over the state of art Corfu. So in this, what it does.
Abinet, I think the authors like it to be pronounced like Scalog.
Oh, okay. Okay. Oh, sure. Yeah. So in Scalog, uh, the client sends the record, so it actually changes the sequence of ordering. So first it sends the data to all the shards, that is the first step, and then each data server sends the uh, a cut, like which says that how many records are there in its primary and backup to this ordering layer, and this the ordering layer then determines a global cut and sends the global cut to each shard. So and then these data server, they have the algorithm to order the records on the basis of the global cut. So this is how this one achieves removes the problem of reconfiguration. So even so there is no mapping this client is maintaining. So there is no downtime in case a read or sorry, in case a shard is added or removed. So even if a shard is like finalized or added or removed, this ordering layer actually like keeps like maintains the previously sent cut by that shard, and sends the same to the other shards in case suppose this S4 is down. Okay, so we'll see it in more details later. Uh, These are some of the design principle of Scalog, which the paper presents. One is auto scaling, that is throughput can be adjusted according to the requirement. Reproducibility, that is all the records in the log should be in order so that it can be reproduced during debugging and consistent failure recovery. Then log must minimize latency, that is the client can should be able to write to the nearest uh, shard. Okay, and then a log must provide high append throughput, and then sequential read should be very read throughput should be high, and then log must be fault tolerant. Then this is the like architecture of Kellog. So this is the ordering layer, this is the data layer, and this is the client. We'll go in detail of each layer. Okay. So these are the few like uh, standard API functions which a client has been provided. Append is basically to write to the log. Then subscribe is basically to read from the log, and there are others as well. Data layer. So this one I'll explain. So data layer, so each data server actually has two parts. One is primary and one is backup. So when the client sends the records to primary sends the records in first in first out order to the backup. And yeah, so this is the data and each shard has multiple data server. Ordering layer. So ordering layer basically determines the global cut as we saw in the previous picture. So it has and how this paper has designed the ordering layer to make it fault tolerant as well as scalable. So ordering layer has two parts. One is this part where the cluster of servers are there which follow Paxos protocol. There's Paxos leader and the Paxos followers. So this is responsible for ordering of the records. And the other part is the aggregator. So since we do not want to overwhelm the ordering layer with the TCP connections, so what we do is what the paper does is it creates this tree-like structure of aggregators, and each aggregator has the um, local cut sent by a particular this data server, and this aggregator propagates the local cut to its parent aggregator. Okay, so thus fault tolerance is achieved by this Paxos, and scalability is achieved by this aggregator. The workflow, that how global cut is created. So see here, there are two shards in this picture. So shard 1 has two data server, shard 2 has one data server, just to like see that how this global cut is determined. So if you see here, there are 4 records in the first one and 3 records in the backup of the first data server, and here are 2 records and 4 records in the primary and the backup. And in the third shard, in this data server, there are 4 records and 4 records in primary and backup. So this one sends 4,3. This one sends second one sends 2,3, and the third one sends 4,4. So ordering layer determines the global cut depending on that. So this so it sees that how many have been persisted, and it minimum cut actually. So it says that 2,3 should be for this shard, 4,4 for this shard. So global cut is 2,3, 4,4, and on basis of that, each data server runs the algorithm which orders the records according to the global cut, and that has been described in the paper, the algorithm. And then evaluation. So a paper actually has evaluated Scalog with the in comparison with Corfu, and also has evaluated 2 applications of Scalog. One is the Scalog store, and one is Scalog. We'll see later on. So this paper evaluates Scalog first on for reconfiguration, that how reconfiguration impacts Kellog. Then second one is that how Scalog handles the failures. Then third on the write throughput and write latency. Fourth one is the read operations, and fifth one is the how the applications perform. That is the Scalog, Corfu, and the Scalog store and Corfu store. So for reconfiguration, so if you see here, what they have done is first by adding a shard, how both the systems behave. So in case of Scalog, the throughput remains constant, but in case of Corfu, there is some downtime, and after downtime, there is a jump in throughput. Then in case of finalizing a shard means the write has stopped on that particular shard, but it can only be used for reading. So if a shard has been finalized, this still the throughput remains constant here, but in case of Corfu, there is certain downtime, and then the throughput jumps, increases. And in case of how failure recovery has been compared, in case of so each component has been like dropped, so that to see that how it behaves, in case of Paxos leader failure, there is some downtime, but there is no downtime in case of Paxos follower fails. How much downtime is there? And there is no downtime, but there is some drop in throughput in case of aggregator failure, and in case storage server fails, there is certain drop, but then again it increases once it's back. And similarly, in case of Corfu, if the sequencer fails, there is some downtime, as we saw the design, and if the storage server fails, there is obviously there is downtime. Write performance. So this one actually has been done for one shard. So for the comparison for one shard for Scalog and Corfu. So since Corfu has the bottleneck, that is the sequencer, so that is why because the client has to interact with the sequencer, so due to that there after I think after 800 or something the write latency increases, but in case of Scalog this remains constant. Write performance, so in versus like write latency versus shard size. So as we saw for one shard, how was the graph? So if we increase, similarly the write latency increases with number of shards, increase in number of shards, because in for Corfu, but it remains constant for uh, Scalog because of that bottleneck of sequencer. Read performance is almost, paper says it's similar with identical for similar paths, but they have studied the sequential read in that section. And now we'll go to the applications. So one application is Kellogg Store. So Scalable store uses basically the Scalog system only. So for if the number of keys, they have compared multi-put. So if number of keys increase, the number the I think this can be called as throughput only, k multiputs per second decreases with number of increase in key. And similarly in case of multi-get, the performance of both Scalog and Corfu store is almost similar. And this is vStore. vStore is actually an object store. So in case of Corfu vStore, they maintain a global log as well as each object has a materialized stream log. So the client has to write to both the global log as well as the materialized log for that object. And in case of Scalog, each object is mapped to a shard. So it does not maintain, I think, separately each log for each object. So there is difference between this writes per second, and that is if you see 18.6K and 13.6K, and I think that is basically due to the sequencer in between for Corfu, but not for Scalog. Yeah, and finally the limitations. So limitations are that Scalog does not provide any policy for adding or removing shards or uh, finalizing the shards. Entire burden of like selecting the shard or adding the shard is on the application. Then second one is in case of frequent failures, steps needed for recovery may complicate scheduling and allocation of resources. And the third one is that the paper current design does not address any security concern with the current architecture. Yeah. So thank you.
Oh, thank you so much. So, Abinit, if you like, you can open the Google Docs for the discussion, and we can try to answer the questions together.
Yeah, just a minute.
And feel free to add new questions while we go through the questions.
And feel free to just ask questions too.
Yeah.
Is the Google Doc visible to everyone?
Yes.
So like I have to go over the questions, or like anyone?
I guess whoever wrote the question reads it, maybe that's better. How does Scalog compare with AWS Physalia? What are the pros and cons for each? So this was a recent paper that also appeared in NSDI 2020. So Physalia, basically, it said that this is basically chain replication, and they have cells for the configuration boxes. And so the chain replication is also sharded. Each shard gets its own cell, and the cells can be reconfigured through normal Paxos reconfiguration means to be placed closer to the corresponding storage servers they are overseeing. So it's a basically structured sharded chain replication approach, and I wanted to see if anybody has anything to say about this approach versus that approach.
I had my interpretation of the Physalia paper coupled with the Scalog paper was that one of the major drawbacks that I saw based on just reading it and not imagining, like just trying to imagine the real world use case was in Scalog, they spoke about ordering layer failures and expecting them to be transient. And therefore, clients essentially are blocked until the ordering layer comes back up. And that means that, and the ordering layer is the piece that orchestrates the global cuts for all the shards. And coupling this with the approach mentioned in Physalia, where the Paxos layers are basically structured so that it's each key has has strong consistency properties. And so if I had a design where I took the cuts for certain shards and arranged those cells in the same network, that would improve my consistency guarantees for certain shards. Like it would improve consistency guarantees per shards in Scalog.
Yeah, I think Scalog provides the global ordering as well. And that's also a topic that we can discuss. How useful could that be? It's useful for some applications, but in AWS Physalia, it was definitely disaggregated. I mean, those are disjoint via chain replication instances. Mm-hmm.
But isn't it the purpose of Physalia was to essentially shard the database into as many fault domains as possible, so that little faults in one part of the system don't impact the other part of the system. So there is never, concern or desire to have any kind of total or total guarantees. It's just to make sure that the failures can be as isolated as possible. That's about it.
Yes, yes, and I think Faisali had nice things that it could be deployed in wide area network. You can do relocation of the configurator with the storage servers. Those are all very nice points going with Faisali. It's deployed in production in Amazon. So I guess maybe it's a more disciplined approach. And part of the reason I asked this question is like,
it's also a different problem, right? Here we still have a single point of failure, which is this ordering layer, right? Until you recover the failure at the ordering layer, you cannot proceed. There, a failure can be recovered, for some shards without effects in other shards. I think they're meant for completely different types of applications.
I don't know.
So I have a question. Alexei, you said here you cannot proceed until you resolve the failure in the ordering layer. But I think that's what they emphasize on, that you can actually do proceed, because writes can still continue because those two are independent.
I think you can take writes, but my understanding, at least looking at what is it? One of their figures. Let me find that figure in a second. Also, for the sake of providing the read your own rights kind of property and linear usability guarantees, right? You cannot return back to the client until you know the order, which means that a client can find the shard, it can write to the shard. The data may be replicated, but then you're still waiting for this ordering to be resolved before you can say to the client that, hey, your operation is in and this is the position.
Yeah, so yeah, that's true. I think
that's a figure 2 in the paper.
Yeah, the ordering, the rights will not be acknowledged, but the clients will be able to continue to write. So I think this whole scheme assumes like asynchronous kind of writes anyway, because even when you have everything working, there's a high latency between the writes and client and the. But I think the difference of this and other systems, at least what the paper says, is that with others, even writes cannot continue. I mean, depends on how you interpret writes. If you just talk about like bulk writes and not acknowledging them, then I think that continues. That can continue. But if your application is synchronous, which means it does a write and waits for it to be acknowledged, then yeah, then.
I think you're correct that if you do the fire and forget kind of style interaction with the system, then your writes at least not going to be lost and they will eventually get ordered.
Yeah.
But if you expect some kind of feedback, then there will be a delay.
Yep.
Yeah.
I want to add something here. I don't think so their ordering service is that important, because if you see the global order which they generate does not affect the whole system, because the global order is just a number. For example, each shards are the ones which are replicated and each shards are maintaining the replica. Even if the ordering service, this paper, I'm not saying they've suggested in the paper, but I think it can be easily modified to ensure that ordering is maintained within the shard level. So if one shard is getting affected, other shards can still continue processing, because there's nothing stopping. I don't see in the whole paper where the global order is actually going to destroy the whole system if one of the shards, if it is not there, because each shard can easily maintain its own ordering. I know they have chosen this idea of having a global, but I don't understand why is it exactly necessary to have that.
You're right. I mean, one partition having problem does not slow down the other partitions. That's a nice thing going for the paper. Only if, for example, one partition of 2 nodes, one is done, the other partition basically can still accept writes, but cannot return acknowledgements for this. And they propose, well, we can finalize and start a new shard another place, and that's one way to recover from that. But the failures across the shards are isolated from each other. And about the ordering thing, it's asynchronous. It looks like it's like watermarking version vectors from each shard. I like the ordering. And they say that it's basically comes free, and if some applications need it, they can use it. And for transactions, it's needed, right? If you are doing transactions across shards, that's a useful thing to have. But it is asynchronous. They say that, well, the ordering layer tries to do this every millisecond also, but yeah, I guess in the same data center, right? So that's one thing, and yeah, still 1 millisecond is not bad, but still latency. Well, 1 millisecond, and then there is, I think, message delays. It should be easily 4 or 5 milliseconds. Okay, so next question, I think this is also from me. How does this compare and contrast with SD Paxos? So I wrote this just to put this in perspective. This Scalog is not solving consensus, right? SD Paxos solves consensus. And actually, in my mind, SD Paxos is the closest in consensus realm that uses a similar algorithm. In SD Paxos, the clients first, again, replicate to the servers, and then the ordering takes place in another coordinator. So SD Paxos also divorces the replication from ordering, and similar as in Scalog, you know, SD Paxos does the replication first and provides the ordering later. So I think they are similar idea, but SD Paxos is in consensus domain, and it's a consensus protocol, whereas this is assuming consensus in the coordinator, in the ordering layer, and provides sharded logs on top of that. Anybody wants to add something here?
I mean, if it's in the consensus realm, what's the point that we are trying to make here? Is it that SD Paxos is similar, but it's gonna have like high latencies, so it's bad, or like what's the comparison?
No, I think SD Paxos solves a harder question,
Yeah.
whereas this assumes consensus and provides maybe a service to sharded logs, a global ordering. But I think of this ordering after replication, it has been around. I just want to make that point, and I also want to make the point that this is not a consensus protocol, but a service built on top of consensus protocol.
Right, of course.
Yeah, I think I'm not familiar with SD Paxos, but I think if the key idea of this paper appears to be do the persistence first and then do the ordering. And if SD Paxos has a similar idea, then it's good to know. And I'm looking, they're not mentioning this in the related work. Yeah, I think that was the key idea. Like I think that's how they how they emphasize it. They say the key to Scalog's singular combination of features is to turn on its head how decoupling has traditionally been achieved.
Yeah, in defense of SD Paxos, whereas they do start the ordering after the replication, it's not strictly after. It's actually like half an RTT after. So it's lagging behind, but it's not strictly after. There is some concurrency between the replication and the ordering that happens in SD Paxos. But yeah, the general like order in which you start is you replicate first and then start ordering.
Also in Scalog, I like that, you know, these shards are treated as, you know, another separate business, like client's business. You can start another one, and it goes into effect in the next watermark, and it appears as a new entry in the next watermark. That's nice. So this can provide scalability to sharding. Actually, this is, I think, tying up to my next question. 3 and 4, maybe let's treat them as same question. This is not consensus. This is log maintenance, and there is also batch component in this, meaning that the ordering later appears, comes to us in batch, etc. At least we learned that. And there is not a real read operation. There is a read with position number, but there is not a like a sticky read about give me the latest version of this. If you are there, learning the read, learning that L before. I don't need to learn the L before and pass it as a parameter. So my question, tying questions 3 and 4 is this good for replicated state maintenance, right? SD Paxos, well, with Paxos you can do replicated state maintenance. Does this approach provide any disadvantages, drawbacks, or makes it incapable to do replicated state maintenance? The paper mentions that this is good for doing, running analytics on the logs because the reads won't affect the writes, etc. And I wanted to delve deeper into whether there is a inherent disadvantage here for maintaining RSMs on top of Scalog.
It's quiet, I guess I'll go then. For the RSM, right? Yeah, the RSM, the replicated state machine, is going to be the application on top of Scalog. So, like I don't see anything preventing this application to be built with the existing API, because all you need, from your node that maintains this replicated state machine is to execute these commands in order. So it needs to read, needs to be able to catch up, and so on. Like it's a lock, it's not an RSM, right? If you're saying that it doesn't provide give me the latest value, well, give me the latest value would be something you expect from a replicated state machine. It means that all this lock has been executed up to this point, and then you can get the latest state of your state machine. But it's just a lock. So if you implement the node on top of it, yeah, you'll have this API. But that's not the problem they're solving, obviously.
Yeah. Any other comments? Yeah. Yeah, it's linearizable, all right, but looks like the reads are always from the past with the L, with the read operation, or just subscribe and you get, okay, these are the logs that are appended. So I'm trying to see if there is inherent disadvantage there for maintaining RSMs using Scalog logs. And or if a fault occurs and shard is...
Yeah, Murat, the same thing is going to happen in your Paxos back replicated state machine. If the node fails, it will need to catch up and read through the lock. It's not going to jump to the latest position right away because it needs to execute all the commands to restore its state, from the snapshot, all the way up. So it's not changing anything.
Yeah.
Next question.
I think that's Suyash.
The question which I asked, I think we have already discussed, but I think I'll go over again. So I think my question was, is there any specific advantage of having this whole global ordering where in the diagram which we saw in the paper and the presentation, there were different shards, and every shard on the ordering rate gave finally a single one order. do we need to do that? I mean, I could see only one use case in the paper, which was during the trim, but trim can still be handled per shard basis. Based on the sequence number of each shard, we can easily maintain the trim. I understand this paper's motivation is to have a global order, but I couldn't understand why is it required in this specific application in which they are treating it. It's a sharded application, and there is no cross-shard transactions notion. Like in databases or distribution, there's a notion of cross-shard transactions, but there's no notion of cross-shard transactions here. So do we need any global ordering here?
You can build application on top of this that does cross-shard transactions. I think the Scalog store, or whatever they named it, has transactions that can be done across shards, right? The multi-put, multi-get. So those are useful to enable those things. But otherwise, you don't need to have a global order. But it's there almost for free. If you use it, it's good. If you don't use it, it's also good because it doesn't cost you much.
Yes, but my only point is if there are a large number of shards, then we can actually save on communication. We can save on communication. We can it can be done in parallel. It cannot. Multiple techniques can be used at the same point of time. It need not be necessarily depending on each shard. Maybe we can do some techniques. That's what the whole idea is. If we remove, we can do it asynchronously. Not every shard needs to be given its ordering at the same point of time. That is.
I think global order is a design goal, and it's not an artifact of the sharded design in the system, but it's a core design goal, such that when I write records to my database, and when I perform reads later, I would always, so in case of if my traffic increases, I can scale up the cluster by increasing the number of shards, but I still have a global order of records across all those shards. And if I didn't have this property, then I would be responsible for, as I scale up a cluster, I would have to figure out how to order records across those clusters. And this gives me, so the core idea being that I can actually get versions. So if it is a simple, I'm writing multiple versions of a given record at a given timestamp, I can give you the latest value, or I can give you the value at a given timestamp. And that is what a global order gives me.
But so why is global order important in this application? Because it is maintaining a log. And for example, the question here is that if in each shard there are specific number of replicas, let's say 2f plus 1 replicas in each shard, then I'm already assuming that I can handle up to f failures. And at any point in time, I can always maintain the per shard ordering. So at any point in time, and if a client requires the information about the current shard, he does not require information all. So the whole shards can never fail if you're assuming a 2f plus 1 scenario. So global ordering is necessary if we didn't have the notion of shard. If we had just all replicas, then yes, global ordering means. But the meaning of a sharded system already means that we don't want to maintain. I understand it's an artifact of the system, but I'm still not understanding why is it a necessity in this design.
Yeah, 2f plus 1 is nice, but even with f plus 1, the order would be useful, right? So the order says, the order from configuration says that this is persisted, so it's good. So yeah, Suyash, I think I also missed something. What is, what about global ordering that you think leads to an overhead here? The global ordering comes asynchronously, and you don't need to wait for other partitions to make progress to get your global ordering. Is there an overhead to the global order that you are complaining and saying that it wasn't needed?
I was thinking if we didn't have global ordering, we can assume for each shard, we can maintain its own set of ordering. Where for that, we can actually separate, or even if you want, we can easily scale up ordering layer. Instead of having just one ordering layer, we can have multiple ordering layers for each shard. And that they can only, and moreover, we can localize the ordering layer For example, if one shard is in, each shards are in different countries, then ordering index could be specific in those countries, so we can easily scale up.
Yep, that's possible.
Yeah, there is a system called Apache Kafka, which does something like that, right? You shard the lock, and you only have the order per shard, right? So you can think of it as just having like multiple smaller locks, I guess. So yeah, as far as Murat, as far as scalability, right? The global ordering does reduce the performance. If you watch the video that they have on NSDI, I think one of the questions was, actually, the question was, well, why do we need global ordering, and like, and what penalty does it give you? And they do admit that because of this write act that has to wait on this asynchronous global ordering to come back to the shards, their writes are a little bit slower than they would be in systems like Kafka. And they want to improve that, so yeah, there is a little bit of a penalty that they admit.
But I would say that in case, suppose it's like a data store, it's Kellog store. So in that case, the entire responsibility of determining that what record lies in the which shard, that logic client has to maintain, right? Like if it is sequential, it's easy to determine that, okay, this shard has max this much, this till this number of records, so I can easily look into it. But if it is like each shard is maintaining its own order, then it's like if you have to read a certain record, you just have to read all the shards and find that, okay, which one has my record.
Not necessarily. A lot of existing database systems, when they use sharding, they apply different techniques. They can be a column-based partitioning. They could be range-based partitioning. You can already partition keys on the basis of range. So what client already needs to know is that what is just the range if each shard is. And moreover, they can be easily hashing technique which could be used. So based on the range, client can already hash that, okay, this is my key, this is what data I want. I'll just hash it up and I'll come to know which shard I want to send. So he does not need to maintain all the data. He just needs to know what is the range. So range
I think in this design, that's like my first question. Usually sharding implies like having a global key space and then dividing that key space, partitioning that key space. That doesn't appear to be the case here. You can the client can specify the shard it wants.
Yeah.
And they mention in a bunch of places that they just choose things randomly. So this is not your typical shard application where you can hash your data and deterministically find out where your data is going to be stored. So also playing a devil's advocate here, I think a global order is like if you don't have a global order here, what is new in this system? Like how will it be different than Kafka?
Does Kafka do replicate first, order next?
It doesn't need to, because it doesn't need to maintain the global order, right? So you just shard. You say, this. I think Kafka shards are like a key range shards, right? They're not like random shards. Here.
In replication, yes.
So you say that, okay, for this particular log, this particular key range is going to go to this shard. You can read, write, done. All the ordering happens per shard, so you don't have to have the global ordering layer. That's not your bottleneck. That's not the point of failure. You're good. You just don't have the global property, right? So I think the question that Yusuf is asking is, what does this global ordering really buys us? Like, are there any applications that can use that global ordering on that scale at least?
Yeah, very good point. Very good point.
Going to another question, which was very interesting, that what is the new? I think one of the most interesting part, I found this paper is very suited for this specific application. This is something which cannot be applied to obviously other domains, because I was trying to see the ease they do, specifically the ease of having the cuts is very interesting about this thing. I have not read, I will not say I've read every Paxos paper, but I've seen rarely any other paper talking about the notion of cuts. And I think cuts is what is giving them the most highest frequency. And yes, fine. And their ability to just switch if one shard fails to another shard without actually, because Kofu example, which they showed, Kofu actually suffers a performance failure, but which this does not. According to me, those two are much more interesting parts than exactly the global ordering, maybe. Because the reason I was thinking about global ordering and all this and this thing, because I was trying to see if can this idea be used in other places, because this was very beautifully done in my sense. So I was trying to see, can it be used in Byzantine fault tolerance? But it cannot, because there are a lot of issues, or you cannot just determine what ordering layer just said in a some simple easy manner like this, or cuts cannot be used in those applications. But this is something which very clearly suits this specific application. It may not perform other cases, but yeah, that is what Kafka clearly does not do that. So that is a difference here.
If you want to try to find out a little bit more about how they make these cuts, right? What's behind them? Try looking for vector clocks and like version vectors. There are quite a few systems that use vector clocks, and this is pretty much what it is, right? So it's a vector clock of the progress of all states. So if you look for vector clocks, find some papers. I think it's going to give you a better understanding of what they're trying to do with their, like how the ordering layer actually works. On top of my head, there is one really old database, well, really old by, I guess, modern standards, that uses vector clocks for ordering, for maintaining the order of operations, and it is called Project Voldemort. I think it was based on like original Amazon Dynamo hash ring kind of stuff, but then they made the ordering within the system with the help of a vector clock. And they don't have this as strong, I guess, guarantees, but they do use vector clocks. So it's definitely not like a new idea to look at each node's progress and record it in a vector and use that for ordering.
Alexei, let's skip to your question, then Talib has a bunch of questions we can do that.
Yeah, I mean, my question is simple, right? I'm finalizing add. This is about the finalizing the shards, right? So if they say that there is a failure, they decide to close the shard. So let's say the shard had two nodes, one failed, you close the shard. So right now the shard is supported by only one node. So yes, you're not writing to this shard anymore, but you can still read from this shard. And now essentially this shard is not fault tolerant, unless I misunderstand something and there is some kind of other protocol that somehow restores the tolerance, replicates it again or something. Right, so
yeah, my understanding is yes, there's just one node left, and if that one also fails, then you lose data. But then you have two failures.
Yeah. Well, yeah, I understand that their system is, for two nodes, it's, yeah, only half can fail, or yeah, one can fail in the two-node configuration. It's just that.
I think it's clever because, right, f is equal to 1, so one fails, you can still do read. So basically they are saying that in the and the one that's already standing can accept the writes but cannot acknowledge them. So start a new shard and copy this into both nodes there and finalize this shard and continue from the new shard. Yeah. I think nice.
At the same time, right? If you're like a subscriber of this system, and you're reading through the shard that has only one server left, and then this server crashed, you're stuck forever.
Right, and you can only read from, yes, but f is equal to 1. And you can only read from that one server to the watermark. You cannot read above watermark because...
But if this one fails, all the clients who have subscribed to the log prior to that shard, they're going to get stuck forever.
Sure, then assume f is equal to 2 and these servers and so on.
Yeah. I mean, it's a minor point. I'm pretty sure they can recover the redundancy fairly easily because it's a read-only thing at this point, but yeah.
Okay, Talib, maybe summarize.
Okay.
questions and
Yeah, I will quickly go over, like, probably skip. This is just I quickly read the paper, and these are some stream of consciousness questions that came to mind. So the first one is, yeah, so it's not your typical sharding where you partition the key space. Yeah, is that what everyone understands how it is? And then this brings a bunch of problems with it. What if, like, all clients start reading from one shard or writing to one shard? How do you start doing load balancing and so on? So do you have to, like, do it manually, like clients, users who are using the system have to be conscious of where to write data, where not to write data? So that brings a whole can of worms that I don't think they ever discuss. Okay, I think we can skip that one because I think we all agree that this is not your typical sharding. And then yeah, they say that their Scalog assumes a serviceable crash rather than fail stop, and you cannot reliably detect crash. So how's this difference is actually implemented? Is this just the fact that the ordering layer will stop receiving the order, stop receiving cuts from the crashed one, and then, like, and then that will just take care of the problem. The clients will detect that they're not getting acknowledgement, and then they will start writing to another shard. And then given the global order, like, I'm not very clear on how this global order is implemented, like, in very much detail, because it talks about each server having an identification number. So if you have, like, say, servers 1, 2, 3, 4, and then 5, 6, you have 3 shards and 2 servers on each shard. And let's say the middle one gets lost or crashes, stops sending updates. Then only 2 shards start sending, and you have a server ordering, like the ordering of the server there. So the fact that you lost the middle ones, does that mean, you know, now the order is shifted and so on?
No,
so I think this, yeah.
You still use the same order, but then there would be no progress from the middle shard. They will still give the old numbers from the middle shard.
So essentially, if you have this fire and forget writes, you know, they may not succeed because now you don't have the full shard, and this sealing of the shard, right, is gonna cut it out at some point.
Okay. Yeah. Let's like take it offline, as they say. So and then my understanding was there's a single log, but then, like, in the architecture part, they say each log consists of multiple shards. Does that mean a single instance of Scalog has multiple logs, or is this just it should have been like a log consists of multiple shards, like a minor nit, I'd say.
I guess a log consists of multiple shards. Yeah.
So and then yeah. So did anyone see any mention about the size of the records?
I didn't.
Yeah, it's 4 KB or something like that.
Oh, 4 KB. Okay. Like, do they have a limit on the size of the record? Because if they have multiple clients doing, like, large streaming records, large records, they have the same problem as the Google file system, which is, like, you cannot have the consistent, you can't provide, like, strong consistency with this if you have large writes, because you need to you know, you need to interleave the writes.
I don't think they claim that they are strongly consistent anyway, because of.
Oh, they do claim. They say
they do.
The strongest.
In the sense that, so the way I interpret it is, like, if a client writes something and then the client disconnects and then reconnects to a shard and requests its own read, it won't get it right away. It may not get it right away.
Yeah, that's but when it.
So I interpreted it as eventually consistent, not strongly consistent. I don't know.
Oh, no. They specifically say Scalog offers fully linearizable semantics, the strongest possible consistency guarantee. That's like page 327, top paragraph on the right.
Talib, can you tell me what's wrong with very large records? Because you can't write it once, so you lose the atomicity. Is that the problem with?
Yes, yes. Yeah,
Sorry,
so
I think I'm missing. Can you explain me what is the relation between size and strong consistency? Why is a large record an issue for strong consistency in this case?
so it's not an issue. It's just you won't be. It will become a bottleneck because you'll need to wait until a single client finishes writing all of its data, and then start accepting the other one, which will
Right.
limit.
But I think this can be handled with the batch processing technique, right? I mean, multiple clients are writing, the packets are coming, you keep on creating batches till the time the request comes, and you keep on processing the next batch. Yeah, I mean, this can be done in a pipeline manner.
Yeah, if you have multi-threaded execution in the shard, in the prime, I guess it could be done.
I mean, you can have multiple threads doing this thing, and it's a common batching technique. Which I think I'm missing something. That's why I'm not understanding
Okay,
how is it a performance.
No, I think you're right. I think you're right. The reason I kind of one thing I forgot about the system is that acknowledgement is not immediate.
No,
So
yeah.
that's why, yeah, I think you're right. The server can just buffer things from multiple clients, and once the write complete, and then do the write, and then because it doesn't have to immediately acknowledge the, yeah, okay, that's good.
Okay, 12.
Yeah, so how does a client choose which server to write within a shard? I guess
it's primary. They within a shard they write to primary.
No, any node is a primary, Murat. There
Yes,
is no a single primary in a shard. You just pick a node, and for that operation, it's going to be a primary.
Primary, yeah, and then it's copied to backup of others using FIFO.
Shard has two nodes, and I thought there was a dedicated primary in the shard.
Per operation.
Per operation.
Yeah,
whatever node I contact is going to be the primary for that operation.
Each replica has a primary and a backup. So anyone can write. So they have both primary and backup at each replica.
So each replica can do both.
Yes.
No, I missed that one. But I guess how does a client choose which shard? That's, I guess, they assume, right? The client.
No. The question is not which shard. For shard, they have like set shard policy, or they choose a default shard. But within the shard, there are multiple servers.
Sure.
How does a client choose which? Yeah.
So your question is there some load balancing they are doing, etc.? But nice question, yeah.
Yeah, they keep saying like they just keep saying we do random, and yeah, I guess they do this one randomly as well.
Okay.
It's just I was wondering if there's some like logic behind it.
Yeah. Your question 13 is also similar to Alexei's, related to Alexei's question after that.
Yeah, so I'm not sure where the global sequence number is stored. Like, do servers store it? Like, there's this sentence in 2.3 saying, using the globally ordered sequence of reports from the ordering layer, the storage server can interleave its log segments.
Sure.
Yeah, so does that mean a server like rearranges the log segments?
Right. Definitely the servers keep this as the watermark because the servers can only serve reads up to that sequence number, their version of their version number in the global sequence. And yeah, that's where that's stored at the store. And we also had a discussion about Alexei. Is this global sequence numbers maintained at the ordering layer at the Paxos shards? I think it should be, but Alexei says it may not necessarily be. Which?
Yeah, I'm trying to. I guess where I'm coming from, Murat. If you remember AWS Aurora, paper, right? So they have a client who, a single writer essentially, right? A single client, like a proxy that has a sequence, right? That just keeps assigning the numbers, integer numbers, logical numbers, right? And when the failure happens, this logical number is never Paxos protected, it's never replicated, it just exists in one machine. And when the failure happens and then a new proxy emerges, it recovers that number from the storage nodes because storage nodes know their sequences. What was the last known sequence? So why do we want to keep Paxos here if we can contact the shards? Maybe we cannot contact the shards because they may fail. That's the thing. So,
I mean, if you are keeping IDs and locations of the shards,
because if I have the shard configuration, if I have the configuration of all the servers,
yeah,
contact them, learn the sequence number.
Yeah, if you are keeping that configuration, why not just keep another integer?
So that's why I was thinking that maybe this ordering is not just ordering, maybe it also keeps the configuration, and you want the configuration to be durable.
Yeah, I think so. Okay, I think we, again, did not have breakout.
I think it was a good discussion.
But we didn't hear from several people.
Yeah.
Hear from more. I think, should we try to enforce breakout rooms for the future, or we still have 10, 15 minutes?
So what is breakouts exactly?
We divide into smaller rooms, 2 rooms, 3 rooms with 5 participants each. And during this discussion, we identify some directions where we can do work in the breakout groups. Breakout groups, basically, there is a guy who is a scribe that writes groups discussion to solve a small problem we identified during discussion. And after the breakout groups, every group reports progress, but we have not been able to do it in the last.
To be honest, Murat, I think it's a lot of overhead. We need to get the questions.
I agree.
And it may not work outside of a classroom, to be honest.
I think if we want to hear from everyone, so everyone can just shout in this discussion section and provide their input.
When it works great because the group of 5 people can do work together better. Right now, I think 5 people talks and the rest are not talking. But so maybe for today's, can we get the other people to say a couple sentences so we have everybody at least participate in that way?
So basically, like when we were discussing global order, like first, like when we were talking about applications which require like global ordering within like different shards, I think I can think of a lot of applications where like, which are like right now, like for example, like personally, like I came upon a problem where some data sets, like I was using Kafka and one of the data sets was stored in a particular shard. Like they were like basically debug logs. And some debug logs were stored in some other shard. Now, when I'm debugging, I actually want to maintain the order between those. So I can like make inferences like what exactly happened before the other one.
Yeah.
And this is essentially
a good one.
Yeah. So
I think the paper mentions that one.
Yeah. So I mean, so that kind of stuff, I can think of a lot of applications where we need global order. But what my question is basically, can we use global cuts as a to kind of maintain the global order and make global order like superfluous? Can we somehow make global cuts like do what I want to do rather than relying on a global order? I mean, I'm just thinking about it. I'm not able to understand the relationship between those. Like, how are both of these related? And if there is no intersection between both of those things, then yeah, maybe we need both.
Actually, I think you have like that particular application is an interesting point because like if you want the absolute global order, right, of all the like debug logs, right, This Scalog may not do it because the ordering within the shard, not within the shard, within each like batch, right? Round trip to the ordering servers and back. So all of these concurrent operations, they are ordered lexicographically. They're ordered by the server IDs and stuff like that, not by like the actual some other order, right? So all this, for example, for the debugging purposes, right? If you have multiple events come into this debug log at the same time, it still doesn't give you the absolute guarantee that they are going to appear in a true order in which they happened in the application, just because this particular login is, the write is long, right? The write is long. All the concurrent writes are ordered in a deterministic, strict way that's not attached to any of the application semantics.
Can you explain it a bit more? I didn't exactly follow.
Yeah, I think I started to lose myself on this explanation. I may maybe we should take it offline and yeah.
Sure.
Mohit, what was your question at the end? I missed that actually.
So basically, like I use Kafka for a particular application where, okay, I'm inputting some debug logs to a particular topic, and it's like on a certain shard. Yeah. And then I'm inputting some debug logs like of a different application which are stored in a different shard. Mm-hmm. Now I want to use both of these logs, bring them together for debugging purposes to understand like what happened, like what's the correlation between those. Mm-hmm. So in that case, this like global order can be like useful. I mean, I can think of a lot of other applications.
Sure.
So I do think global ordering is like makes sense for a wide array of applications.
Yeah, mm-hmm. I think it can be added to Kafka also. I don't know. No, maybe too much work because they need to remember and insert at the record at the same time. Maybe through a third process that does this, subscribes to both and pushes a record of the order periodically to each log.
Okay. Still not gonna do it.
Not gonna do it?
I mean, you can have some order, but it will not be linearizable from the client perspective.
Sure. Yeah.
I mean, and my follow-up question was sort of like that maybe global cuts can be used to kind of like instead of global order, but I don't exactly understand the relation to be like, okay, maybe we can make global order superfluous and be like, okay, I'm going to rely on global cuts in some manner to make that correlation.
Yeah.
So, I mean, I do think global order is relevant in those kind of applications. Can be useful. But I don't know what, I couldn't completely understand what Alexei was saying. So if we can maybe.
Cool, okay.
Yeah.
You can write it in the discussion. We can also offline provide something. Let's use the Google Docs for things that we don't tie up, and because people later revisit the Google Docs and provide some explanations, so it could work. Arjun, do you want to say a couple things?
I don't really have anything to add, but I did find the discussion around global cuts very interesting. I'll definitely, I mean, are there other papers that use this sort of technique?
I mean, there's vector clocks, version vectors that Alexei mentioned in the Voldemort and related databases. Databases uses these vector clock trick a lot.
That I've seen, but I had sort of never seen this sort of.
Streaming systems also use a watermark trick, which is sort of related.
Okay. Awesome.
Yeah, Michael.
So most of my comments that I'd written on the paper had to do with the sharding, questions around sharding as well, and we trod over that territory quite a bit.
Cool.
Yeah, I guess one thing that I found interesting there was that I don't generally expect whole shards to be garbage collected usually, like sort of like objects might be. So I thought that was interesting, but yeah, I guess my main questions are more around why they called that particular division shards, or
Yeah.
I mean, it seems to be just sort of like a general memory abstraction, maybe.
Okay, cool. Yep. Mohammed, from database perspective.
I don't have much comment about the paper.
Okay. We did Mohit, we did Piyush.
I don't have a lot of comments this time.
Okay. Salim?
I don't have much to add, but just one question: how is this going to be related with the blockchain?
Could be related. It's a nice technique. So yeah.
The question is how to make it, Byzantine, right? This really assumes a very well-behaved environment, both for the clients and for the shards and everything.
I think this will not work very well with BFT protocol. Clients will just destroy this system because there's a huge dependency on clients, and moreover, the global sequencing is just on the basis of some numbers which each replicas are sending. If some replicas are malicious, they might just send different numbers.
Yeah.
So I mean, in the BFT system, the ordering is done on a request digest. There is no mention of digest here. There are no signatures. I mean, even if we add it, it's not easily possible that this can actually, this as it is will not survive so easily in BFT system.
Right. So actually, this could have been a good breakout room discussion. So people interested in Byzantine fault tolerance could brainstorm ideas related to this for 20 minutes, write some things, have some dead ends, but then something comes up. So breakout rooms are good for these kind of questions, but we have been late. I think Vikram, Vikram is remaining.
I think Alex brought up this point just right now. My a feeling that I got while reading it is you're kind of hoping for the system to behave in a certain way in some kind of idealistic scenario. So for example, like they've said that at the time that the ordering layer is down, the system would delay the acts to the client. But in a real world use case, if there is a high throughput service, the client cannot be blocked for that long. Otherwise, basically the client is going to be client is going to be a bottleneck, and then that's going to crash. So then the client needs to know that the shard is not and the client cannot distinguish between the ordering layer being down versus just that particular shard having some network issues. And so the client doesn't know if it needs to reconnect or not, if it should try. So I felt like this operationalizing the system might be more tricky than it seems. That was a feeling that I had when I read it.
Yeah, good point. Yeah.
So what are the big challenges?
So imagine that Scalog, the system, is having some kind of issue. So the client connects to a shard, and then it sends a bunch of messages, and it's not going to get an ACK until the shard basically gets a proper sequence, global sequence for those messages.
Right.
Shard may not be able to get this for multiple reasons. One is that the ordering layer is down. That is, and the second is, for example, there is a network partition between the primary and the backup itself, and it's trying. So basically, it's not even being able to talk amongst the other storage servers, and then the client doesn't have any clue. It's just sent messages and it's blocked, and it doesn't know if it should be retrying or if it should be attempting a connection to another shard. And since this is a high throughput system, the client could be overwhelmed and crash just because it is queuing up messages. So in that kind of scenario, a part of me felt like it would have been nice if if Scalog returned this sort of error, and say it is an ordering layer error, the client can decide if it should if it should just drop or if it should connect to another storage or whatever shard.
So AWS Faisalia does a lot of engineering work to handle these questions.
Yeah.
They had very detailed discussion of those, and for a big production deployment, I think that has advantages. Yeah, a lot of advantages. Abinit, if you like to maybe say a couple closing sentences, then.
Yeah, so I have, like everyone else, I have been using shared log in the service oriented architecture where there are multiple machines serving the same service, and there is a like load balancer on top of it. So when you see a shared log, a shared log serves quite a crucial role in that, and I'm not sure that whether global sequencing will play a crucial role there. Maybe that has to be analyzed, but yeah, and it was an interesting paper altogether, and easier to read as compared to the last one.
Yeah.
Yeah.
Okay.
Yeah. Thank you.
So next, thank you so much for the presentation. It was a great presentation. And next week, I think Suyash is doing the atomic commit and.
Yes, I would be doing that. Thank you.
Okay, cool. So Alexi will open a channel and you can share some content there over the weekend.
Yes,
okay.
I will do that.
Okay, good. Thank you so much, everyone. And, next week we will do this. What was the name of the paper again? The Unifying Consensus and Atomic Commit paper from VLDB 2019. And the week after that, there is a paper called Stable and Consistent Membership at Scale with Rapid. This is ATC 2018 paper. This is from VMware. That doesn't have a presenter. If anybody is interested in presenting that paper, it's just take 20 minutes of presentation before discussion. Just volunteer in the Slack channel, okay? Or volunteer now and we will be happy. Guys.
I'll do it.
Oh, who is this? I will record.
Yeah.
Mohit, oh, thank you so much, Mohit. Thank you.
No problem.
Good. Good. Okay, then see you next week, Wednesday at 14.
Same time.
Okay, bye-bye. Nice discussion. Thank you so much.
Okay.
Thank you. This was great.
Yeah.
Bye.
Nice
Bye.
everyone.
Bye-bye.
Bye, everyone. Okay, I'm